So as Magnus said, I'm going to talk about this ridiculously long title, which, as you can see by the initials, is fairly contrived. So, scalability, consistency, replication, availability, and performance. I've had lots and lots of questions about BDR, so I am going to talk about that in some detail during the talk as well. So it's not just a general talk. I have to have some words at the beginning to say that some of the work that I'm talking about is funded by research projects that require me to state that the funding has been received from them, but that doesn't apply to all of the things that we're going to talk about. So it's only for fairly selected areas that we're talking about. But I'm still required to tell you that. So let's start off with a little bit of thinking at the beginning. We've got this thing called Brewer's cap theorem, which says that out of consistency, availability, and partition tolerance, you can have only two. The usual problem being nobody knows what the third one means. So I've decided to invent a theorem of my own, which is the scrap theorem, which lists all those important keywords there. And the theorem is basically whenever there's n experts in the room, we have n+1 opinions. Which is my get out for anybody asking questions, especially difficult ones. But the important corollary of this theorem is that actually it's possible for greater than one of those things to be true. The main determining factor in your use of replication technologies of various kinds is really what are your business requirements. And so quite often people argue about which is better, this or that, and it's easy to come up with cases in which any particular technology has a particular advantage. So that is the enduring reason why there are so many replication technologies, because it's just not possible for a single one to fulfill all business requirements. So please remember that when you're talking about this subject, because it's easy to kind of get hooked into one you like, one you don't like, and such matters as that. Yeah. And please feel free to call that the Riggs's scrap theorem. So. Good. Oh God, it's been tweeted already, is it? Oh my God. So. Okay. So the first thing to talk about is scalability, and there are many aspects of that. People normally break it down as read and write scalability, but even that kind of trivializes the level of detail that you need to talk about things at. There's one other major aspect to talk about, which is single query scalability. So we end up with business intelligence situations being quite different to online transaction processing scalability. There's different considerations there at least. What I'd like to do is just to have a look at some basic points around the scalability. So I've just come up with a kind of very simple architectural model to allow us to discuss that. So if you imagine that we've got a sharded database with 4 nodes, and there's a single well-defined shard key, so that the data is evenly or roughly evenly spread across those 4 nodes. Okay, so these are not fully replicated databases. This is a single data store spread across multiple nodes. Now, in that situation, you can see that if we've got a select statement that's fairly simple, along the lines of select something from a single table where the key is set to a particular known value, we can calculate which of the nodes that known value will be on and then we can make a single node request to retrieve the data. So in that particular case, and this is where I get to use my laser pointer, because it's an equality request, we can hash the value of x, and we can calculate which node it's on. So that is a particularly interesting style of request, because if we're able to concentrate our requests down to a single node, it means that we have potential to run more requests when we run on multiple nodes. And that is an important characteristic, in the sense that we're able to scale our workload above that which is capable from a single node. Okay? So that's the basic principle that the many different systems use. Many of the NoSQL approaches use roughly this concept in order to achieve write scalability. And that's basically where we're going to have to head as well if we want to achieve write scalability. So that's basically the principle on which the future is based. I'm not going to talk too much about that today, but you can see that what we're working on today is aiming in the direction of eventually being able to solve that kind of query across a distributed data store. Now, when you're asking a different kind of question, then the actual SQL ends up producing a different kind of a plan. So if you're accessing a table where you're saying a non-key value equals y, or worse, something like non-key value is greater than y, you can see that that's actually going to affect not just a fairly distinct set, but actually a wide-ranging set of data. And the end result of that is that it's going to be a multiple node request. Now, if you're doing a business intelligence type query, having that single query spread across multiple nodes is potentially a very good thing. But if you're trying to write a high volume application that's receiving and supposed to be handling very large numbers of requests, an all node request is actually the worst thing that you can get, because an all node request obviously requires all nodes. And that means that if we add nodes to the database, it's not going to get any faster. And what that means is that the speed of replying to this single request may well be speeded up by adding nodes. Okay? But our ability to handle more requests does not increase. Okay? So our ability to handle OLTP style workloads is not increased when we have all node requests. So in order to build a scalable system that can handle OLTP systems, we need to get some way of restricting the query down to less than all of the nodes. So the point I'm making here is that an application is actually the thing that is scalable. We can deliver a scalable database platform, but if the application itself is not scalable, then you cannot scale that application even if the underlying database is capable of supporting it. So a scalable platform may be defeated by a non-scalable application. Now, one of the benefits that has occurred in the NoSQL world is that by restricting the types of requests that you're allowed to submit to the system, you can actually guarantee that the application comes out as scalable, because you're only allowed to ask certain types of request. Now, we have the difficulty of, if we're going to support SQL, then we need to be able to determine whether an SQL statement is scalable or not. And by scalable or not, I mean, would it access multiple nodes or would it access all nodes? Now, obviously, that depends upon things like the shard key, the type of planner that you've got, the type of indexing that you're using. So it's actually quite a complex challenge to work out whether an SQL application will scale. And there's only really, at the moment, one way to do that, and that's to physically test the scalability of an application. And that's actually what I would view as one of the limiting factors from PostgreSQL's scalability perspective, is that it's difficult to tell whether an application, just by looking at it, is going to be scalable. So that's one of the challenges that we've got certainly for the future. So the point I'm trying to make here is that not everything is scalable, but some things are. So we do have to provide options that will allow multiple node scalability in the future. And what I would say is that my experience from trying to build these systems over actually a 30-year period is that supporting scalability is quite hard in some applications, because people always say, oh yeah, it'll work, it's completely scalable, my application. And then you kind of find out that actually it isn't. And it's very difficult to write an application that over, say, a 5-year period will stay scalable, because there's always some business guy that thinks up some clever request that will prevent that scalability. So there's really some challenges there that we have to address. And in true Postgres fashion, we are going to address them fully and completely, and that means it is going to be really a multi-year journey to implement some of the things that we're talking about here. Some other points to make about consistency. Distributed consistency does require some kind of distributed transaction manager, and that lends itself more to tightly coupled systems. It's also quite difficult to mix workloads and maintain consistency across nodes. Replication allows you to have loosely coupled systems, and the things that I've learnt through mistakes and observations in my early career is that tightly coupled systems, and I'm really thinking of Oracle RAC is where I got my experience in that regard, don't work really quite as well as they're built, and that loosely coupled systems are really the way to go. That's why I've spent a lot of time working on replication options rather than the more cluster style of system. So the replication options that we have at the moment, we've got Sloaney, Londeast, Picado, and of course streaming replication. And what we've been working on is what we call logical replication. The difference between logical and physical replication is that with physical replication, we are simply directly applying the changes listed in the transaction log records, in the WAL records. With the logical replication, we're talking about interpreting the transaction log, reading data from the transaction log, and then formulating change statements. So that might be generating SQL statements, or it might be something else entirely. So in the 9.4 release, we have the feature that's called logical decoding, and that allows us to read the transaction log and generate a change stream that can be applied in various ways. So that can be used for generating changes through to a different application, or what we're looking at doing is to make that work for what we call logical replication. Now, the reasons that we want to do that is that primarily the physical replication does come with quite a few restrictions, and rather than work through all of the restrictions, when you look at what those restrictions are, it would take as long to lift those restrictions as it would to develop the much more useful capability of logical replication. So what we've been working on is something called bidirectional replication. obviously with the implication that the data can flow in both directions from one node to another. And that's otherwise known as multi-master replication. But we chose the term BDR because what we wanted to do was illustrate that multi-master replication is kind of like building a cluster. And what we're building here is kind of like a toolkit that you can use to actually build significantly complex systems, not just a single coherent cluster. Oh my God. Get away, get away. Is this...
Oleg wants a picture.
Do I have to get photographed with this? Oh my God. How embarrassing.
Right. Thank you, thank you.
Yeah, I wonder what that was, right? Scared. Yeah, okay. We need a verb for that rather than a chelnik. Is that? Can it be a verb? This is America. We can just make it a verb. Been frosted. Yes, I like. That works. So, I mean, like you've spoilt it now. You've right in the middle of BDR. Okay, so basically, what can we do with BDR? Well, the current system that we've built, you can have up to 48 nodes, all working together, all sending their changes in different directions. Okay, why 48? Well, we just like kind of ran out of money trying to test it. We figure it kind of goes a little higher than that, but we, whoever's got a requirement for more than 48 nodes can probably pay for the test. So we tested it up to 48 nodes, works just fine. There's a couple of things that are pretty cool about it. Obviously, it's got efficient change capture. That's what we've put into 9.4. But what we have also designed into it is efficient apply. So it doesn't execute SQL statements on the target nodes. It actually uses a much lower level facility. Okay, and as a result, we get significantly higher performance and throughput than we would have done otherwise. The notable things about the BDR implementation that we've gone for is that we've got transparent global sequences. So there's none of that business about having to set up one node that starts at 1 and another node that starts at 10 million, and kind of God help you when you get to 10 million on the first node. So sequences are basically completely transparent in this setup. We've also done a considerable amount of work to make DDL replicate in the middle of a data stream. So you can do a very complex series of transactions, like you can insert a load of data, add a column to that table, insert a load more data, remove a different column from that table, delete a load of the data, and then do something else, and it will all just sail through. Okay, so that you don't need to kind of stop the system, pull loads of levers in order to get the replication to continue working, and then kind of kick-start it again. It will just continue to work as a flow. The aspect of physical replication that it handles DDL beautifully is something that we wanted to replicate here, and that's actually what we've done. So the implementation that we've gone for is actually has got these two quite major features in terms of usability. So it's not just logical replication, it's logical replication plus sequences plus DDL. Okay. So who's using it? Well, these are the two that I'm allowed to tell you about. McAfee, now known as Intel Security. I can't really tell you anything other than that. They did go public that they were funding it, but obviously I'm under confidentiality to describe exactly what they're doing. There is another company that we're able to talk about more publicly, Bullion by Post. These guys sell gold bars on the internet, and if you look here, you can buy kilos of gold for like $40,000 and things like that. And if you want, you can actually buy a gold bar, and they will come around with a security van and give you your gold bar. It costs about $300,000. I haven't bought one. So that's who's using it at the moment. I'll tell you a bit more about some of the other applications. But in terms of throughput, what we wanted to do was aim for a system that was almost as good as physical replication. And that's pretty much what we've achieved. You can see there's a kind of 5, maybe as much as 10% drop in performance when you're using the logical replication, and that is obviously significantly higher than can be achieved using trigger-based systems. So that's throughput. Now, what we did here is, obviously, it's possible to just run a load of stuff on one node and go, that's fast. But what you've got to remember is that it's asynchronous replication. So you've got to measure a steady state where all of the nodes are coping with the data that's coming from the other nodes. So testing the performance of these things is not trivial. Okay, if you do a trivial test, it can look even faster than this, but that's not a valid test. So these tests are sensibly valid. What we have also measured is the latency in the sense of what's the replication delay between one node and the other node, and again we have significant advantages over other replication mechanisms. Okay, so this is so we've got performance advantages in both throughput and latency. Latency with regard to replication delay. Okay. Now, there's another customer that I'd like to share with you what they're doing. I can't tell you the name, I can't tell you what they're doing, but this is their main business system, and they have 4 different nodes, Singapore, Sydney, Johannesburg, and somewhere in the UK. And by setting up their database in this way, they have a different form of latency advantage in that all of their users spread across different parts of the world have got immediate fast access to a database system. The alternative would be to have users in Australia basically making cups of tea every time they press a button on their system, because it's going to have to go all the way to the UK and then all the way back again. Okay, so by doing this, this company is able to have user groups split up all across the world, all of whom enjoy direct and immediate access to the databases. Okay, so it's actually a very significant thing for them to be able to use their application anywhere in the world. So they're now able to expand internationally by setting up new distributorships, new places where they can sell using this technology. Okay. Well, and as well as getting high availability and other such things. So this is what we're saying is the benefit of BDR. So when I say the latency word, that's actually being used in 2 different ways here. There's the latency of access to your local node, which is an application latency, and there's also replication delay latency involved, and both are good. Okay. So a couple of things. BDR does not yet do write scalability. Okay. So it's not possible yet to add multiple nodes and run workloads on multiple nodes so that you end up with a higher total throughput through your application. Okay. Now it's been reported to me in some areas that that has meant that people are are telling others that BDR can't cope with large databases. Well, it certainly can. That's nothing at all to do with the capabilities of BDR. So big databases are fine. What we don't yet do is write scalability. Now, that is something that's on the roadmap. We haven't started to code that yet, but it's something that we aim to deliver in the longer term as part of the BDR project. Okay. So what are we working on right now? We're currently working on selective replication, so the ability to replicate something less than all of the database. Okay. Now you might think that's a really important feature, and it is. That's why we're working on it now. It's just that actually getting the data down the pipe was kind of more important. So we did that first. The Axel project, which is about analytics on extremely large European data, is funding online upgrade. It's funding it to a certain extent. Whether we exceed that budget remains to be seen. I guess we probably will. What we're trying to achieve there is a tool that will allow us to upgrade databases between major versions. So we have the core support now in 9.4. So what we're saying is when we get to 9.5, you'll have a tool that you can press button and easily upgrade from 9.4 to 9.5. Obviously that doesn't work at 9.3, it's only 9.4 and above, but once you've got to 9.4, from that point forwards, we will be able to support online upgrade for you, okay? So that's what we're hoping we'll get into 9.5. So what I wanted to talk about now is how all of this is coming about, the project plans and such like. So at this point, BDR has already taken 2.5 years. We started it in something like October, November 2012, and it will take a long time yet to integrate properly and carefully all of the things that have been done to date. Okay. So what people are telling us is that they want solutions now, but they also want future integration. Okay, so every single person that talks to Second Quadrant is saying longer term integration is what we want to see, and that is one of the clear reasons why we are fully supporting a single open source version of PostgreSQL, i.e. we are not attempting to fork Postgres. What we're doing is concurrent integration. So we're bringing some of these software solutions forward for use now, but we are working on plans to as to how to integrate these things. And this is not kind of the first time this has been discussed. You know, the plans that we have are hopefully clear and discussed for everybody in the community. So what deliverables have we got? Well, there's three main deliverables that we're bringing forward for your use, and those are BDR, UDR, which I'll explain in a minute, and contributions to Postgres core. I've written 9.5, but obviously that might be 9.6 or 9.7, or I don't know what happens when we get to 9.10. That will be confusing. So what is BDR? Well, obviously stands for bidirectional replication. It's a spoon of Postgres. So it's, yeah, okay. So there are some light changes to the Postgres core code in order to make the replication work. Okay, it is not an extensive fork, and we're not looking at that as a long-lived thing. Okay, this is a way of releasing the code for people's use now, well, it's in production in various places and it's working. Second thing that we're releasing is called unidirectional replication. Now this is a subset of the BDR code. Now the subset that we're going is defined not by a particular set of features, but it's defined by this will work on stock 9.4 Postgres. Okay, so the intention here is to produce a cut down version of BDR that will just plug in as an extension to 9.4. Okay, so it will be a module that you can literally say create extension UDR, and then it will begin working with 9.4. We're working on that now. I'm not going to discuss the exact release dates, but soon means months, not years. Okay. And we're hoping that that will also contain selective replication. So what we mean by that is the ability to say, I want this table, but not that table. That's the first implementation of selective. Later selective is I want these rows from that table, but not these other rows. Okay, so there's kind of a future plan for what we might put in. But the first version of UDR will be table level specific replication. Okay. In terms of the implementation that we're going for, now that we have dynamic shared memory and such like, we're working on a version that will literally plug into Postgres without needing to restart Postgres, which is where we are at the moment. So anyway, so UDR, who likes the name? No, me neither. So yeah, no, okay, you're going to put your hands up now that I've said I don't like it. So. It's basically a working title. You know, we thought of some names, but I mean, you know, we're not exactly marketing-led in our thinking here. Yeah, so we've got BDR and UDR, or the other one. The third thing that we're working on is possibly able to be called UDR 9.5, and this is a version of UDR that won't work with 9.4. It requires things that are in 9.5 to work. So this is a kind of slightly changed version of UDR that is a submission for use with 9.5. Okay. Subtle difference between the two. Basically, what we're saying is UDR is a module that you'll be able to use fairly soon in production. UDR 9.5 is the kind of future version that you'll be able to use in the long term. Will you be able to tell the difference between them? No, not really. It's just under the covers stuff that's going to be different. Okay, so it's really just a you know, sort of version number of the code. This is the thing that we're aiming to put the online upgrade aspects into. Okay, so when you get to 9.5, this will be the tool that you use to upgrade your 9.4 database to 9.5. Okay, so those are the three main deliverables that are coming out of the work that we're doing. And if you're getting the idea from here that this is a major project with lots of people working on it, you're absolutely dead right. There's at this point, we're probably sort of 3 to 4 man-years of effort gone into it, and we've got basically 3 people full-time working on it, plus other people contributing aspects to the code at various points as well. So can you see that slide from the back? Okay, it's gone a bit dark here, so. So what I wanted to do here was present to you a kind of graphical representation of the things that we're working on and how they relate to each other. And this idea of a software stack that's basically slowly building the feature set, and that each time we add a feature, it's adding on to what's gone before. So what we had done over here is we built replication transport, we built physical replication, and then on top of that we added hot standby. Okay, so that's what allows replicated standby databases to be used for read-only slaves. Now, what I'm saying here is that is pretty much the pinnacle of that particular line of the evolutionary tree in terms of replication. I'm not intending to do major work on extending that technology. We are doing some work though, so it's not dead, it's not unusable or anything like that, and obviously it's going to be maintained for a very long time. So it's still going to be completely usable, and it's also very appropriate for a wide range of uses. Okay, so that's not changing. But what we are saying is that all of the things that we want to do in the future of distributed database actually come out of the logical replication subtree, so that we're actually building on that upwards towards a range of other solutions. So we are building logical replication on top of logical decoding. So the difference between the two is logical decoding sends data and logical replication receives that data. That's why I'm using those two different phrases. And then on top of that, we've got DDL replication, multi-master. Now these green things are things that we have now or are delivering soon. And then in the future, we're working towards automatic sharding, massively parallel query. Those are the things that are in the horizon that we're reaching towards. Okay, I have to say we're not exactly close to them right now, but that's kind of where we're going with this architectural branch of the software stack. So I hope that kind of gives a little context to the stuff that we're working on, at least. So. Just so that you know that all that work that you've spent making your replication work over the years is not all going to be completely trashed. Just to say, if you just leave your systems as they currently are, it's still going to get better over time. 9.4 does have some significant and useful enhancements to physical replication. 9.5 will as well. There's some efforts to look at WAL compression. We're currently working on incremental base backup, and there's been a whole range of patches, and there'll be more associated with improving the performance even better for physical replication. Okay, so your current systems will still continue to get better in 9.4 and 9.5. All I'm saying is that we're not going to be doing massive, major feature development on that kind of conceptual branch of replication. Okay, so I hope I've explained that clearly. So that actually kind of brings me to the end of what I wanted to talk about. But I've got at least one other slide and the ability to answer questions. So if anybody would like to ask some questions about my lovely diagrams or any of the things I've said, now's the time. Okay.
One of your slides mentioned that you were going to do some sort of automatic conflict resolution and things like that. Can you expound on that a little bit more?
Yeah, that is implemented in the BDR that we've got currently released. It's got automatic conflict resolution.
What does that even mean?
Right, okay. So if we have, for example, a replicated table with exactly the same data on two nodes, if two people update the same row in that table at the same time on the multiple nodes, then what will happen is the changes could potentially conflict. I mean, obviously they might accidentally update it to exactly the same data, in which case there's no conflict. But if one person sets it to A and the other person sets it to B, then which update do we take? So what's been implemented is conflict resolution, in that we detect that there are two potentially conflicting changes to that data, and then we have the resolution mechanism is to pick one of those two data rows, but because it needs to be resolved in both places, we need a resolution algorithm that is similar in both places. So we can't just randomly pick one of the rows, because that would end up with a divergence between the two things. So we provide what's called last update wins as a default resolution mechanism, but we've also implemented conflict triggers that allow you to define more exactly how that should be handled. So in some cases, you've got applications where there might be a delta change. So one person adds 1 to something, another person adds 1 to it. The resolution that you'd like is +2 to a particular value. And so you can set up a conflict trigger that would detect that and then handle that delta. Okay. So we've got basically, it's automatic, so you don't need to think about it. But if you care about how it's coming out, then you'll be able to manually change that as well. Alongside that, we've also got the ability to log conflicts to a table or log them to a file. We've also got the ability to log not just the conflicting change, but the whole conflicting transaction, so that you can see what caused that conflict and where it is in the application. So you can actually design around that if you need to. So I believe we've attempted to make it a full and complete implementation, so it's actually useful in the real world. I don't doubt that somebody will think of some ways to extend that, but yeah, so that's what we have at the moment. Thank you for the question.
So when you say last update wins, though, how do you determine the result? Is it timestamp based?
Yeah, it's timestamp based, so you do need clock synchronization between nodes. So.
Is the clock synchronization handled through any of what you're providing? Or?
No, that would just be NTP based. So yeah, it does need to be set correctly across nodes. I mean, it doesn't need to be set exactly, but obviously the closer the clocks are together, the finer the resolution of conflict detection that we'll be able to achieve. So, sorry, there's a question from the guy directly behind you. So when I kind of pointed at you, you both thought that was so okay, go.
That was a conflict, and now we've resolved it.
Okay, cool. Automatically.
Yeah. When the conflict is resolved, how does the loser get notified that you lost? And is that inside the transaction, or is it after you?
That's the difference between logging and handling. So what would happen there is it would get logged that it occurred, but the application itself doesn't get some kind of notification. If you wanted that, you could set it up with a conflict trigger, but then you'd have to have the application waiting in some way to do that. So that's why you can also log your conflicts to a table, because then you can have an automatic program that would process in some way the conflicts that occur. But typically it's some kind of either an application developer, oh God, I've made a mistake, or it actually reflects some particular business process that needs to be handled differently. So we don't want to just chuck them away. So, sorry, questions, please, there.
First of all,
Hi.
I would say that I've been trying extensively VR with the session in our group, and it's absolutely great.
Cool. Thank you very much. Yeah, well, I'm glad you didn't spot any of the bugs that we've had then, because there's been a few. So yeah, I mean, this is new, complex software. We have had a bunch of bugs. but it is open source, and you know, we're going forward with the view that you know, this is for everybody. So it will take some time to get to stability. So.
I still have a question about the feature. It's precisely about the conflict resolution. I've considered before about using consensus protocol like Access or RAP for handling the conflicts, to avoid the conflict.
Yeah, I mean, you can implement that if you want via the conflict triggers. We've got there's an agreement protocol that we use for the way that the sequences allocate chunks, but we don't specifically have any sort of Paxos type stuff in there as to how to handle it. But that's because we're handling it after the fact. A lot of the systems that have sort of Paxos type handling they're systems where when you ask a question, you actually ask multiple nodes what the answer is, and then you resolve what happens when you get two different answers back. So we, in terms of the way the BDR is working, you connect to one database and you ask one answer. You ask one question and get one answer. So we don't have that same requirement. In the future, there might be something where you could connect to multiple places, ask the same question from 5 different nodes, and do it that way. And then we wouldn't need to handle the conflicts in the way that we do.
But I think it happened precisely because the conflict resolution strategies like classical wins, because as long as they're based on timestamp and depends on the time synchronization,
Yeah.
you actually get answers if the talks that are correctly synchronized with happens differently too. So I think it
Yeah, I mean, you know, I wouldn't hide from the fact that it's an area of problem for basically any system, and sometimes you can do that in a kind of eager way in the application. At the current implementation, we are using post-transaction commit resolution. Okay, other mechanisms are possible in the future. So, you know, at the present time, that's what this does. So. I'm not saying all other mechanisms are inferior. You know, just back to what I said before is, you know, there's horses for courses. You know, there's no best way of doing something except in the context of a particular application. Sorry, rather than take your question, there were some other ones over here. So.
Do you have any master node in PDR over all years? Conflict resolution, who is actually working for it?
Well, the conflict resolution occurs in multiple places. It just occurs in a similar way in multiple places. So there is no master node that resolves things. So, yep.
On a selective replication in BDR and UDR, does it allow the slave database to have rising logicals?
Yes, very much so. All of the nodes in a BDR cluster, by the way, we looked for a better word than cluster, so some people call it a flock, and I don't know, but anyway, yeah, so all of the nodes are writable, which means that you can have temporary tables, you can have, you know, anything you can do on a system where you can execute write transactions works with BDR.
Well, context is that in our case, we use something called microstrategy for BDR.
Yeah.
It wants to write to a schema in addition to being able to report against the master table or the tables.
Is that for the scheduler or?
It uses metadata to optimize its own compute processing as it uses.
Okay. Yeah, certainly I've used MicroStrategy in the past, but I wasn't sure what aspect would require that in that sense. But yeah, that's good. I mean, there's lots of reasons why people want to write things to databases, and they just don't work with hot standby, but they will do with BDR. So that's one of the exciting things about that. So, was that Jim that had a question, or?
I was just going to say that a group of elephants is a herd.
Yes. We could go with herd. Anyway, we argued about that and we couldn't work out. So we just went back to saying cluster because we had. It's oh dear, it might. Okay, right. So gentleman at the back there. Sorry, not you. The one at the back there, please. I can't hear you at all, actually. That's probably good if I'm out of time. Do you want to have a question?
Thank you. All right. Well, I wanted to start with, this is great work. We wanted to see the project go in that direction, so congratulations. One of the slides mentioned about BDR not supporting write scalability. You're not talking about concurrent writes on multiple nodes because that's already there. Are you saying that single write cannot be broken out on multiple nodes? Is that what you're referring to?
Well, let me go back to what I've said. This is clearly a point of some misunderstanding. What I'm saying is that if you've got two nodes, if you've got one node and you can do 100,000 transactions a second on that one node, right. If you have two nodes in a BDR cluster and you attempt to do 100,000 transactions on each node, then what you will generate is a massive traffic between the nodes. And what then each node has to do is it then has to cope with its 100,000 and the other guy's 100,000. Okay? Now, obviously, that will be a physical impossibility. Okay? So what will happen is the write rate will reduce on either node and you'll hit some maximum that basically isn't twice what one node would do. You know, it's possible that through various efficiencies that you might get better than 100%, but I'm not promising it, and I'm not saying it's always 1.2 or something. It really is quite application dependent. So it's possible, but what some people think is they say, well, one node does 100,000, I need 1 million transactions per second, therefore I need 10 nodes. Well, that doesn't work on any system I've ever worked with. It certainly doesn't work on things like Mongo, but there is some sort of calculation to be had. So at this point in time, we haven't got that kind of 10x type of scalability. But it's not restricted to database size. It's just simply that all changes are propagated to all nodes. Now, in the future, when we change that so that all changes are not propagated to all nodes, we will then achieve write scalability. Okay? So that doesn't occur yet. It can occur in the future. We just haven't done it yet. Okay? Is that it? Are we there? Perfect. Thank you very much. Just to say that there's various bits and pieces that we've got. We've got some brochures on bidirectional replication, and you're welcome to stop by the booth and talk in more detail to us. Thank you very much.